Okay, let's take a look here at our next unit, starting with chapter 22 here, entitled Inferences About Means. This is, again, as you were forewarned. In the previous unit, we were looking at categorical variables, where, again, the only fair way to compare one category to another is by calculating a proportion of the whole. Here in this unit, we're switching to quantitative variables. And again, if we have a lovely sample size, then we can figure out what the mean is because it's quantitative. Okay, so this is a distinction that you're going to see over and over and over again here. This is not inferences about proportions. This is inferences about means. Okay, so again, we talked about confidence intervals and we talked about hypothesis testing with proportions. So we're going to go through those same ideas, but different type of variable, we have to treat it differently. So random samples are drawn from any population. The population has a mean of mu. Okay, so again, be aware of these specific Greek letters. The population mean is mu, and the population standard deviation is sigma. We could calculate very easily the mean of our sample, the y bar or x bar. You'll see different Roman letters there, but with the bar over it is a sample mean. If it has a sampling distribution with the same mean as the population, and the standard deviation is sigma divided by square root of n, again, n is the sample size, we can say that's our lovely little formula. Notice a very, very different formula than what we use to calculate standard deviation for proportion. So no matter what population of the random sample, the shape of the sampling distribution is approximately normal if you have a sample size that's big enough. The larger the sample size, the more closely the normal works. So we need a random sample and we need the true population standard deviation. Wait a minute, hold on. If we already knew the real population standard deviation, wouldn't that imply that we also know the true population mean? What are we doing all this testing for? Why are we taking samples? Well, yes. Frequently, we do not know the population standard deviation. So, how do we proceed? We estimate. Instead of calling it the standard deviation of the population, we're going to refer to it as the standard error. See that down at the bottom there, the standard error of our sample. Okay. The best we can do is estimate that population parameter, standard deviation of the population, sigma, with the standard deviation of our sample statistic, S. So that's all we've done there is change standard error from sigma divided by square root of n to standard error equals S divided by square root of n. And then we can proceed from there. Hold on. It doesn't quite fit though. The shape of the sampling model changes and it doesn't fit the normal model very well. Doesn't fit exactly. We need to come up with something different. Enter William S. Gossett. Many, many years ago, he was an employee of, yes, beer, the Guinness Brewery in Dublin, Ireland. He was in charge of quality control, basically, is what we would say today, taking samples of batch after batch of their brewed beer and testing it in various ways and then trying to compare one batch to the information that he had about all the previous batches. And he kept using the normal model. I mean, what have we talked about in this class? And it never quite worked. It didn't work as well as he had hoped, as he had been expecting. So, what he came up with was a slightly different model that fit his data better. Now, again, you'll see this in a couple of different ways. It really should be called Gosset's T. At that time, when Gosset stumbled across, this need and developed his own model, the Guinness Corporation had prohibitions on their employees making money basically that didn't go straight to Guinness. So Gossett decided to publish his information under an anonymous name. He knew if the Guinness people found out, he was using his time at work and developed this, and now he's publishing it, and now he's making money off of when he was working on their clock, they would fire him. So it was published under a paper written by a student. How's that for generic? So this model became known as students T. And again, it's a whole family of related distributions here, depending upon what we know as degrees of freedom. Now, we mentioned this once or twice when you did a distribution earlier from an example problem. The calculator spits out at you that DF. That's degrees of freedom, and we'll talk about that a little bit here, and we'll talk about it much more later. The shape of it depends upon the degrees of freedom. Okay, so a standardized sample mean, when the conditions are met, we'll talk about that in a moment, will follow the student's T model with, here's a key thing, n minus 1 degrees of freedom. Okay, so whatever your sample size, subtract 1, that's what we say the number of degrees of freedom is. And our t-score there looks quite a bit like a z-score, doesn't it? Again, you're going to take the sample mean minus the population mean, and we're going to divide by the standard error, that's SE, standard error of the sample. And again, we estimate that by taking S divided by square root of N. Um, Yeah, going back to what he did with the normal model, there's extra uncertainty here for means, and that margin of error just got bigger and bigger and further away from the normal model. But by using this new model that he developed, we get much more accurate results. So, for our confidence interval, just again, starting off simply here with a 1 simple random sample, collecting quantitative data, we can come up with the mean and then use a t interval as the basis of our confidence interval. And again, the formula looks amazingly like what we did before with a sample proportion. Now we're going to take y bar, which is going to be, again, our sample mean, plus or minus, okay, just as we had a Z star, depending upon what we wanted our confidence interval to be, 90% or 95% or whatever the case was. And then we multiply by the standard error. And they keep giving you this formula over and over again for what the standard error is. Hopefully, boom, that's gotten drilled in already. All right, so let's talk about that T shape. The T curve looks an awful lot like the normal curve, but again, the numbers are slightly off. It's unimodal, it's symmetric, and it's bell-shaped. But depending upon the number of degrees of freedom, well, here, take a look. The dotted curve that you see there is the normal curve. The solid one there is the T curve when there are just 2 degrees of freedom. Okay, so again, if you can focus on that solid one, there's much more area under that solid curve once we get out to the extremes. So they say that the tails are fatter. Okay, but again, very similar shape. Don't worry, this is also programmed into your calculator. Um, as the degrees of freedom increase, the T models get closer and closer to the normal, to the point where we could say if it has an infinite number of degrees of freedom, it is the normal model. Um, oh, another big name in the history of the development of statistics was Fisher. Um, and this guy was a character. Um, After his death, there was an obituary published for Sir Ronald A. Fisher. And if I remember this correctly, it started off by saying, now, mind you, this is an obituary. In an obituary, you're trying to describe what the person was like, maybe list some of their accomplishments. Um, you're supposed to speak kindly of the recently deceased. And for this what became a very widely circulated publication that dealt with a lot of the developing world of statistics. They said that Sir Ronald was a nice enough person as long as you agreed with everything he said. And that was the nicest way that they could put it. Okay, Fisher was difficult to work with. And yeah, the Gossett T model, students T, is accurate. It is correct, but he criticized Gossett because there are some assumptions that he made that Fisher wasn't quite sure of. And these are the same assumptions that you need to write down. Again, some of these are repeats. So we got the randomization condition. Okay, that this should have resulted from a simple random sample. Um, Again, if this is without replacement, no more than 10% of the population. You've seen those before. Um, the nearly normal condition, the data comes from a distribution, I'm sorry, the data, plural, come from a distribution that's unimodal and symmetric. Um, yeah, if n is less than 15 or so, maybe the normal model is the better. For moderate sample sizes, say between 15 and 40, the T model is the one that we're going to use. Again, if you look at the data distribution there, if it's unimodal, it's reasonably symmetric. If once we go beyond 40, T methods are terrific unless it's extremely skewed. Okay, so less than 15, we should maybe consider going back and using the normal. Between 15 and 40, you're fine. If the sample size is bigger than 50, we are golden. So I've got another graph for you to look at here. And again, hopefully you can tell the black one, yes, that's black, the one that has the highest peak, that's the normal distribution. Okay. The red one, which really jumps out, I think is really obvious, that's the T model with just 1 degree of freedom. The blue one has 2 degrees of freedom. The green one is 5. The yellow one is 10. So again, as we're saying here, as the number of degrees of freedom increases, we get closer and closer to a normal model. But we do get slightly different values. That's why we can't use the normal model with sample means. Once we get out to, those extremes out there where, it's 3 standard deviations or even 2 standard deviations, you can see things flip, okay? That say even the 5 degrees of freedom, the green one, is above the normal model at the tails. So yes, in the back of your textbook, in the little booklet that I have handed you to use during your tests, there's a table for the normal distribution based on your z-scores, and there is a completely separate table for the t distributed, students t. Okay. Um, and again, it's not too tough because it's listed there as you look for degrees of freedom. Okay. Um, and then figure out what you want your cutoff point is. Again, if we're looking for a 90% confidence interval and there were a sample size of 24, you see on the far left side over here, sample size is 24 minus 1 gives you degrees of freedom. Sorry, sample size is 25 minus 1 will give you degrees of freedom is 24. And again, we want a 90% confidence interval, remember, so this will be 90% here, which means our cutoff will leave 5% here and 5% there. So you read across that top to the 0.05, and then we come down. That's our T star value. If we were going to use the table. So again, I kind of glossed over this stuff here. For this, we're looking to write a confidence interval. Okay, so again, 90% confidence interval, we get 5% on the tails on either side there. So if our sample size was 25, our degrees of freedom is 24. You can do that with the calculator. All right, let's look at this example here. 2004, a team of researchers published a study of contaminants in farmed salmon. Fish from many sources were analyzed for 14 organic contaminants. They expressed concerns about the level of contaminants found. One of those was an insecticide called Mirex that has carcinogenic properties, could be toxic to the liver, kidneys, and endocrine system. And again, it's an insecticide that's probably sprayed on land and then gets washed into the water that is used to raise the salmon. One farm in particular produced salmon with very high levels of Mirex. After those outliers are removed, summaries for the Mirex concentration in parts per million, yay, we need units of measurement, for the rest of the farmed salmon are, here we go. So the sample size was 150. The sample mean was 0.0913 parts per million. And the sample standard deviation, all right, that's the S, not theta, sorry, not sigma, is 0.0495 parts per million. What does a 95% confidence interval say about Mirex? Calculator time. All right, so you go to your standard calculator screen. statistics, go down to confidence intervals, and now in not a z interval like we did before, go down to option number 2, the t interval. Okay, and then you should get this screen that pops up here. And enter the information that we have. Now, again, Texas Instruments has its program, so it's X bar. That's the same thing here as Y bar. So with this first blank, you type in the 0.0913. SX, that's our sample standard deviation, so you type in the 0.0495. And of course, it's the sample size. Here it's 150. And we want a confidence interval. They said 95. Remember, this is a menu here where you can pull down different options. Okay, then click on OK, and again, it'll spit all of this stuff out at you here. Look at that last line. Okay, again, our sample size is 150. For right now, we're saying degrees of freedom is simply n minus 1, so that's why that number is 149. The X bar, that's what you typed in. It figured out the margin of error, the ME. You really don't need that. If we're writing the confidence interval, it's those C lower and C upper, those numbers that you need. Again, just leave them in decimal form. There's no problem with that. We really don't need to be addicted to changing it to a percentage. We're 95% confident that the mean level, again, make sure that you're not saying proportion, the mean of the level of Murex concentration in farm-raised salmon is between 0.0833 and 0.0992 parts per million. Again, for something like this, it's really important to include that units of measurement. Don't just put down the numbers without context. You guys wouldn't do that. Okay, so again, the z intervals for confidence intervals is programmed in. The t proportion is right there. I'm sorry, if you go back to this, look at what we're going to do next. A 1 proportion z interval is another way that you can do that. We can do all kinds of stuff. The t is programmed. Again, interpretation there, it's not, for something else. Don't say 90% of all students sleep between, these two numbers. It's not about individual values. We're not saying we're 90% confident that all students, not 90% of the students. We are 90% confident that a randomly selected student will sleep between those. Again, it's about the mean, not any one particular individual value. In that case, they're examples of students. The mean amount of sleep is this much, 90% of it. No, the true mean doesn't vary. It's a single number that we're trying to capture. The confidence interval is supposed to encompass that. That mean value is going to be different with different samples. Don't say 90% of all samples will have a mean sleep between this and this. It doesn't set a standard for every other interval. It's no more likely to be correct than any other interval, but not less likely either. Okay. 90% of samples of the same size, that would be a better way of saying that one. 90% of intervals that could be found in this way could cover the true. No. All right. But say we are, or if you want to do it individually, I am 90% confident that the true mean amount of students is between these. Make a picture, make a picture, make a picture. The only reasonable way to check the nearly normal condition is to look at a histogram. Um, Can keep going. A one sample t-test for the mean. Okay, so now we're talking about hypothesis testing. Again, we write the null hypothesis, trying to keep it as neutral as possible. We're going to use the same standard of error. We're going to use the same number of degrees of freedom. And we're going to use a one sample t-test to get a p-value, just like we did before. Example. Again, going back to the farm-raised salmon. They found the mean concentration of Mirex to be 0.0913 parts per million, standard deviation from the sample 0.0495 parts per million. Again, exact same numbers that we saw before. As a safety recommendation, the EPA recommended screening value for Mirex is 0.08 parts per million. Well, there's our cutoff point. That's where we need to check. Are farm-raised salmon contaminated beyond that level? Again, we've already checked the conditions. Sample size is big enough. 150 is definitely more than 40. We're okay with that? Remember that 40? Okay, so N is 150, degrees of freedom is 149. We have our Y bar, which again, with your calculator is going to be X bar. And we have the value for the standard deviation of the sample. So for the hypothesis test, we're going to say these fish meet that standard, that mu is 0.08. The alternative hypothesis, this is again where we can put in what we're actually concerned about. We're concerned that that value is greater than the 0.08. We're hoping it's not greater than. We're hoping that it's equal to or maybe even less than. That would be great. But what we're testing here is the fish from this one particular location. Are they a problem? So again, you would write this stuff out by hand. You would show, okay, the T with, again, the degrees of freedom becomes now the little subscript there. And we're going to get not a z-score, but a t-score of 2.825. And yeah, hold on, let's talk about that. So again, we go stats, not confidence interval this time, not really stat test. One way we can do it here is by just going to our distribution menu that we used so many times before to do number 2, the normal cumulative distribution function. We used number 3 for the inverse normal when we had to work our way backwards and find out what the z-score was to find, one of those and find the sample size, for example. This time, again, different variable, we're going to go down not to number 2, the normal cumulative distribution, but number 5, the t cumulative distribution function. Okay, so again, you'll see then the lovely window pop up like this, where, again, they want to know lower bound, upper bound, and degrees of freedom. So again, if we've already calculated our t value there of 2.825, and we're looking for, is it higher than that? We would put the 2.8 blah 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 here and the upper bound as either infinity or maybe 10. The degrees of freedom here, again, you need to type in the specific number. 150 salmon, so degrees of freedom n minus 1 is 149. Okay, so again, you see that values print out here, and then here is our probability that this would happen at random. That's our p-value here, just like we did before with confidence intervals. Okay, now we'll talk about that, the interpretation of that, or again, this is one way to use your calculator. Again, with statistics, distribution, and the t cumulative distribution function. Or we could go statistics and go down to the stats test. And this time we're doing a t-test, not a z-test. Don't go to the prop. Don't go to the sample. Go to t-test. It's option number 2. Don't go too far down. Okay? Again, the prop is short for proportions. We're not doing proportions this time. We're doing means. All right, so again, in this case, our null hypothesis has a mean, mu0 is 0.08. Our sample turned out to be 0.0913. The sample standard deviation, 0.0495. Again, these numbers came from the statistics. That came from our null hypothesis. And carefully, just put in sample size this time. It will automatically subtract 1 and give you degrees of freedom. You don't have to worry about that at all. And what does the alternative say? Is it greater than? Is it less than? Is it not equal to? Okay, remember up here, the default is just saying not equal to. You will need to change that based on what the alternative hypothesis says. And then it gives you a very short result here. So again, it's a t-test. We're going greater than the t-value. Again, that's your t-score as opposed to z-score. This is the one we want. We want the p-value, the probability that something this extreme or even more extreme would happen just at random. Okay? Now, I've been going through this very quickly. Don't know if you're pausing and backing up the video here. Here, our probability, if we go, say, to 4 decimal places, 0.0029, compared to when we use the t distribution function, 0.0027. Okay, so there's a slight difference in those methods. Does that difference affect the outcome? Well, not in this case. Again, if we're saying the alpha level is 0.05, it doesn't matter which function on the calculator you use here, we are going to draw the same conclusion, that the p-value is so low that we reject the null hypothesis and we proceed from there. Okay? We reject the null hypothesis and say, hold on, in farm-raised salmon, the mean Mirex contamination level does exceed the EPA screening value. You don't eat that fish. And who's ever running these farms, you've got a problem that needs to be cleaned up. It is statistically significant, does not mean it's practically significant. It's usually a good idea to combine. If we're looking at a whole situation here about, okay, are these salmon farms in trouble? Well, let's look at both the confidence interval and the results of the hypothesis test in tandem. Again, it's the same numbers, it's the same kinds of calculations. The confidence interval contains all of the null hypothesis values that we can't reject. It has all the plausible null hypothesis values. The ones that we would kick out would be 1 minus C. So 95% confidence interval is that 0.05 level on a significance test. Confidence intervals are naturally two-sided, so they match with a two-sided hypothesis test. Okay? And again, our margin of error, not the Z star, but the T star. Now this one, no, we're going to need the calculator for this. For the Z star for a 90%, it's the same every time. For a 95%, it's the same every time. You can memorize, and some of you have memorized those values. The T values change depending upon the number of degrees of freedom. And that could be just about any number you can imagine. That's going to be impossible to memorize those. Okay, so again, the technology is absolutely important here. Um, Again, before you crunch anything, make sure the sample size is large enough to give you a good chance of being able to find out the answer to the question. Here's a great one. How big of a sample size is big enough? Company claims this program will allow your computer to download movies quickly. No, we're not talking about pirating. You're going to pay for this. This is legitimate stuff. We'll test the free evaluation copy by downloading a movie several times to estimate the mean download time and say we want to set a margin of error of about 8 minutes. We think the standard deviation of download times is about 10 minutes. So how many trial downloads are we going to have to run? We're going to set this as a 95% confidence interval, the margin of error of 8 minutes. Sorry. Sepelia is having a dream right now. So if we just kind of, we have to start someplace. Okay, so if we go back to our 86, 95, 99.7 rule and say we're going to use a Z star of 2. Okay, we're going to start off with a very simple equation here. Okay, so again, we're saying the standard deviation is of the entire thing, the sample, no, sorry, not the sample, the population standard deviation is 10. We're going to use a Z star, which in this case is pretty close to a T star number of just 2. We're trying to get a rough estimate here. How big is N? How big of a sample size would we need to get our margin of error? So that's ME. Get the margin of error down to 8 minutes. Okay, so yay, do the basic arithmetic there. So we're going to take both sides and divide by 20. We're going to take the reciprocal, and then we're going to square it. So n turns out to be 6.25. Well, I'm sorry, 6. How can you download something 6 1/4 times? That's kind of small. Okay. So round that off to 6. That means we have 5 degrees of freedom to substitute an appropriate T star value. Okay. So again, we use the Z star up above just to give us a starting point here. So at 95%, the T star value with 5 degrees of freedom is 2.571. So we go back and we solve that equation again for margin of error. 8 is equal to 2.571 times 10 over square root of n, which again, do the algebra there. So we'll divide both sides by 25.71, take the reciprocal, and then square it. So we're saying here to make sure the margin of error is no larger, we'll round that up this time. So n is 11 times. So to get a margin of error of only 8 minutes, we're going to have to run this and download the movie 11 times. Again, we're not going to stop the download in the middle. I'm not sure how you calculate. Let's not do that. Let's just round things off to nice whole numbers. Okay, degrees of freedom is really a more complicated thing than I've been explaining so far. Okay. Uh, the standard deviation, again, you're going to take the actual minus the mean, sorry, the predicted value. You're going to square that. You're going to add all those together. You're going to divide by the sample size, and that'll give you deviation. And then you take the square root, and that gives you variance, v. And then you take the square root of variance, and that gives you the standard deviation. Yeah, but we don't know mu, so we're going to use either x bar or y bar. Um, the estimate of n minus 1 turns out to be incredibly close to that value. Again, I think this is something that Gossett kind of stumbled across. He's like doing these complicated calculations. Again, this was more than 100 years ago. So he's doing these complex calculations by hand there. Do you empathize with him a little bit more? No handheld Texas Instruments calculators for you guys. And he's like, I'm really slaving away to do this, and I'm getting a number that's just ridiculously close to just n minus 1. All right, so what could go wrong? Again, we've switched from proportions to means. Skewed data, yeah, that's going to be a big problem. You can exclude the outliers, but make sure that you report that they do exist. Um, Biased sample, there's no kind of calculation that'll fix it. Make sure that you're checking conditions. Is it random sampling? Are we taking less than 10% of the population? Um, Again, confidence intervals are tricky. Don't overstate it. It's about the mean of the population, not about the mean of the samples, not about individuals in the samples, not about individuals in the population. Um, so again, different kinds of things. It's a different model that we need to check. It makes a big difference if we have a relatively small sample size. Once we get above 40 or so, I think we're okay. And again, our central limit theorem, our standard error, degrees of freedom. Pretty much the same things that we did before, but again, slightly different model. All programmed in your calculator, you should be fine. Um, yeah, sometimes here, I like this one. If they, on the test, describe a situation and they print out the summary statistics, um, they wouldn't have proceeded to produce the summary statistics if it had not met all the conditions for the central limit theorem. Okay, so that's a safe assumption to make on that AP test or on my tests too. If I give you those, what the mean is, the standard error, the margin of error, the p-value, um, that would not be done with something that was illegitimate in the first place. And that's it. So do your best, take a look at the problems that I put on OneNote, and I will get rid of that entirely and see you guys hopefully soon.